you can send me the recording afterwards.
Okay, I think it's working.
Thanks, Amethyst. Thanks a lot. Okay, so today I'll be presenting a work that we've done with Joe, Arnaud, and Yu-Yang, and that we've entitled Alpha-divergence Variational Inference Meets Importance Weighted Auto-Encoders, Methodology in Asymptotics. So the talk's going to be divided in, say, 4 parts. First, I'll give an introduction and, give the setting, recall the basics of alpha-divergence variational inference. Then I'll move on to the so-called VR-IWAE bounds. I'll try to persuade you that this is the object of interest in alpha-divergence variational inference. And then I'll propose, within this section, a study of this VR-IWAE bounds. And then I'll move on to some numerical experiments, if we have time, before giving you some concluding remarks and some perspectives that remains in the topic, in my opinion. All right, so let's go with the setting. We're going to consider a model with joint distribution P theta of x comma z, which is parameterized by theta, and where x is an observation and z is a latent variable, which is going to be valued in RD. In that case, the pursuit density of my latent variable z, given my observation x, is of this form, that is to say, I've got the joint divided by the normalizing constant, which is the integral of my joint with respect to z. What we're often interested in Bayesian inference is to be able to compute or sample from this pursuit density. And a key example of that, which is going to be central to the work that I'm presenting today, is if we're trying to maximize the marginal log likelihood with respect to theta. This marginal log likelihood, I've denoted here by L theta comma x. You're going to see it during the talk, so it's good to have the notation. And it's just the log of my normalizing constant, so the log of the integral of my joint with respect to z. Why am I saying that in this example? I do want to be able to sample or compute like my pursuit density, is because if I try to maximize my marginal log likelihood, it's very likely that I'm going to be interested in the gradient of this marginal log likelihood. And in fact, if you compute the gradient with respect to theta of the marginal log likelihood, and you do like very simple calculations, you obtain this integral at the end, which is the integral of, with respect to my pursuit density, of the gradient with respect to theta of the log of the joint. So I see that either I would like to be able to compute this gradient, or at least estimate it by sampling according to my pursuit density. Unfortunately, and this is like the typical Bayesian statistics problem, for many important models, I don't actually know how to sample from this pursuit density, so I need to find another way. And in my language, another way is like, let's use variational inference methods. So for those of you who might not be familiar with variational inference, here's like this slide is just to give the few insights that will be required to understand the talk. And so basically variational inference in the context of what we're trying, its main idea is to construct what I will refer to as variational bounds. That is to say, surrogate objective functions to the marginal log likelihood that are easier to optimize. I've seen that it's difficult to try to maximize my marginal log likelihood. So let me try to find an alternative objective function which will be easier to work with. A key ingredient when you try to construct a variational bound is the variational family. We're going to work with the variational family of probability densities that are denoted Q. In the context of this talk, and as a general example, this variational family is going to be of the form I've written there. So I'm going to have Q phi of z knowing x. So I will depend on a parameter phi, which will evolve in this space here. All right. So we have like common examples of variational bounds. And if you've seen like Variational Inference 101, your most common example is the evidence lower bound. So I've written it here using our notation. My evidence lower bound is going to be the integral with respect to my variational approximation of the log of some weights, where the weights I've given their definition here. They are the joint divided by my variational density. So basically what you need to know, like what you need to see here is that usually the joint, we're going to assume this is something that we know how to compute, and the variational density is something that we choose. So the weights are something that we assume that we can compute, and we integrate with respect to this, so we'll be able to estimate this quantity. So I'm saying this is an evidence lower bound, but it can be easily checked if you just apply Jensen's inequality to this integral, and you will in fact obtain that the evidence lower bound is indeed a lower bound on the marginal log likelihood. So this tells you, okay, we kind of want to try to work with this evidence lower bound and to try to optimize it with respect to theta and phi in order to optimize our marginal log likelihood. So this is the most common example. There's another example which might have a job, which is called the importance weighted auto-encoder bound, and which was introduced in a paper by Burda, which is very, very famous in 2016. So this importance weighted auto-encoder bound, IWAE bound, is a generalization of the evidence lower bound, which is defined as follows. So basically, in a high-level perspective, what you do is that here you are integrated just with respect to Q5 of Z. Now, in the IWAE bound, you're going to have Z1 up to Zn latent variables, and you're going to integrate with respect to product of Q phi of Zi here. And then in the log, instead of having just the weights, you're going to have the log of a weighted sum of weights, if that makes sense. So you can see that this is a generalization, because if you take n equals 1 in this bound, you will recover exactly the evidence lower bound. This is a lower bound because if you apply again Jensen's inequality, you will have an inequality of this form. So the IWAE bound is indeed a lower bound on the marginal log likelihood. Why was this of interest in the community? Well, as it turns out, as you increase n, you tighten the bound. So people were always interested in reducing that gap between the bound that you have and the marginal log likelihood, because this is your objective. Everything's clear so far? Good. Joe is nodding. Thanks. That's good to hear, Joe. Okay. So this is like kind of, I was telling you, okay, this is an objective function that you use as a surrogate, and you're hoping that this is easier to optimize. So the next question is, how is this optimized? So in the context of the paper by Burda and co-authors, basically training with the IWAE bound relies on 4 steps. The first step is to be able to approximate your target. Okay, you're looking at like the IWAE bound. I'm going to look just at the IWAE bound because it's a generalization. So what I'm saying here works also for the evidence lower bound when n equals 1. Okay, so I'm looking at my objective, and I want to first see whether or not I can track this objective. So it turns out that the answer is yes, because I can estimate this objective function by just sampling according to Q phi n times. Okay, and I've got this unbiased estimator. So tracking my my quantity of interest that I can do. The second ingredient that we're using in this paper is the reparametrization trick. Is everyone familiar with reparametrization trick? Yeah, okay, good. So if I use this reparametrization trick, then I can write down the expression of the gradient of my IWAE bound using the reparametrization trick. And the last step is then to observe that this gradient can be estimated in an unbiased manner by the expression here. So I can perform my stochastic gradient descent procedure and hope to have some sort of convergence guarantees. Okay, so those were like the basics, and now we'll be like, okay, we've seen 2 bounds, but are there like other interesting variational bounds in the literature? So there's one which is super interesting because it has an alpha in it, which is called the Variational Inference bound, and which was introduced in a paper by Lee and Turner in NeurIPS 2016. So this bound, like I teased, depends on an hyperparameter alpha, which is taken to be non-negative and positive, and which is different from 1, and it reads as follows. It's this expression. So I've got 1 divided by 1 minus alpha, the log of the integral with respect to my variational approximation again, multiplied by my weights that are taken at an exponent 1 minus alpha. So the weights, they are the same as before, but I've recalled them here in case you've already forgotten them. Okay, So this variational ring bound that they've introduced, why did they introduce this bound and why did they find it interesting? Well, the first thing is that, okay, it's still a lower bound on the marginal log likelihood. So, you know, it's still potentially a good candidate for marginal log likelihood optimization. It has the property that when alpha equals 0, it's the marginal log likelihood. So okay, it's tied to the objective we're trying to optimize. And if I let alpha go to 1 in my variational ring bound, I recover the traditional evidence lower bound. So the message is sort of that by introducing this variational ring bound, we're working with the flexible family of variational bound, which are indexed by this alpha, and which enable us to interpolate between the marginal log likelihood, so our objective, and the evidence lower bound. I'm going to leave this, I'm just going to mention it briefly, but this variational ring bound is in fact tied to another divergence. If you're a bit familiar with variational inference, you know that there's Kullback-Leibler divergence involved. And in fact, if you work with the variational ring bound, you're working with a generalization of the Kullback-Leibler divergence, which is called Rennie's alpha divergence. I can give more detail if you ask about me later. Okay, so this is my other bound. I've got interesting properties, and now I want to know how I train this in practice. So I'm going to follow Lee and Turner in their NeurIPS paper, and I'm going to give you the 4 steps that I was giving you before. Okay, the first one is having a Monte Carlo estimators of the VR bound. They're giving this one. The second one is to reparameterize once again. Third one is to write down the reparameterized gradient of the VR bound, which is given by this quantity. When I gave the talk in Cambridge, I tried to get one of the participants to write down the expression, but I was not very successful, so I might not try that again in the context of that talk. And lastly, I need to have an approximation of my reparameterized gradient so that I can perform stochastic gradient descent. And the one they consider is this one. Okay, so we've got a training procedure, but let's take a few seconds to sort of analyze what's going on here. So the first thing that we want to do is, because we've seen that when you take alpha you let alpha go to 1, in this expression, you recover the evidence lower bound. You kind of want to do a sanity check and to check that, you know, when you take alpha equals 1 in your gradient, you do recover the gradient of the evidence lower bound. So this means that the extension you're performing is also valid for the gradient. Okay, so it's true. So we're a bit relieved. The second thing that is important is that if you train using this procedure with alpha that is less than 1, you will obtain empirical positive results. So this is one way to motivate working with this extension. Like it does improve what's going on in practice. In the context of the paper of Lee and Turner, they do see that it plays a role. However, and this is a big however, there are a few problems with this procedure, which you might have seen or not. The first problem is that, you know, I just gave you here is an approximation of the DR bound. However, this approximation is biased. So you might say it's not that big of a problem, but compared to the IWAE bound we had before, now we have a bias when we try to approximate our objective function. The second problem, and I'd say this one is worse than the previous one, sort of, is that the approximation of the gradient that is written here, I also told you here's the approximation. Well, this approximation is also biased. So this means that when you're doing your stochastic gradient descent, you're not doing unbiased stochastic gradient descent for which you have theoretical guarantees. You're doing biased stochastic gradient descent. And in their paper, they're not really justifying why this procedure should work and at least converge to something that, you know, makes sense, as it would be the case with the IWAE bound. Lastly, and this is just kind of because, you know, a bit of a detail, but if you look at the case alpha equals 0, it is a bit surprising, because if you take alpha equals 0 in the VR bound here, I've told you before, this is the marginal log likelihood. However, if you look at what's going on in the stochastic gradient procedure, if you take alpha equals 0 in this expression, you recover stochastic gradient descent for the IWAE bound. So there's a bit of a mismatch. You're looking at a stochastic gradient descent, but if you're look at the objective function, it's not the one you would expect. So this was like, this made us a bit curious. So like, okay, there seems to be a mismatch when alpha equals 0. All right. So Lee and Turner, they didn't address all of these problems, but at least they were aware that it was not nice to have bias in the estimator and in the stochastic gradient descent, and they looked particularly in the first problem. So what they say is like, okay, let's look into the properties of the biased approximation of the VR bound that we have. And more precisely, they were like, let's look into the expectation of the biased Monte Carlo approximation. So this means that here is my approximation, and I'm looking at it in expectation. So I've got 1 divided by 1 minus alpha, and then here's my expectation. It's becoming like a product. Is it making sense to everybody? Joe is like, yeah, this is good. This is good stuff. So they were like, okay, let's at least try to understand what's going on if I look in expectation at my biased Monte Carlo approximation, which makes sense, okay? And they proved a few properties. The first one is that if you play with n, if you increase n, then you've got this kind of relationship. So as you increase n, in fact, you get closer to the VR bound, which is satisfying in a sense, okay? It tells you if you keep on increasing n, you're getting closer to the VR bound, to your targets in an increasing manner. And in fact, if you let n go to infinity, you recover the variational bound. Okay, so that's what they proved. But we're like, interesting, this expectation that we've introduced. And in particular, we noticed these two things. If you let alpha equal 0, and this bound, this looks very much like the EY bound I have shown you before. Is everybody seeing it? Yeah? Chris, you're like, yeah? Okay, so we see that when alpha equals 0, I've got exactly the EY bound. When alpha goes to 1, so I'm not going to prove it, but it's true. If you let alpha go to 1 in this quantity, in this expectation, you recover the evidence lower bound. And at this stage, you're like, okay, could this expectation, what they define as the expectation of the biased Monte Carlo approximation of the VR bound, should it be the object of interest? Could this be seen as a variational bound? And building on this kind of ideas, we are coming now to the paper that we've written with Joe, Yu Yong, and Arno, and for which you know the name. I'm not going to repeat it. But basically, we're trying to see now that there might be a connection with this alpha-divergence variational inference methods and importance weighted auto-encoder through this quantity that we're going to look into in more detail. Okay, so this brings us to the second part, to the VR-IWAE bound. So now I'm gonna define it, and basically I'm going to revamp this expectation they were introducing in Lee and Turner in 2016, and I'm going to say this is actually a variational bound. So for all alpha, which is between 0 and 1 excluded, I'm going to say, let's look at this quantity and let's see what kind of properties we can get. So the first property is that the VR-IWAE bound is indeed the lower bound on the marginal log likelihood. So when I was saying, should I look at this as a variational bound? Well, yes, it's a good idea to do this because in that range of values of alpha, it is a lower bound on the marginal log likelihood. And even better than that, it can be estimated using Monte Carlo approximations. And this time, this is going to be unbiased. Everybody agrees with that? Yes, very silent crowd. Thanks, Dan. So it can be estimated using unbiased estimators. So my problems that I had with the VR bound has now disappeared for just the estimation of my target. Secondly, if I reparameterize, I will observe that I recover the same stochastic gradient procedure as the one I had with the VR bound, but this time using unbiased estimators. Okay, so here's the expression for the gradient of the VR-IWAE bound. And if I just use Monte Carlo samples, I obtain an unbiased estimator of this gradient. And lastly, this was like the surprising part from before, where I say, okay, it's a bit weird what goes on with alpha equals 0. Well, now we have the theoretically sound extension of the EY bound, because if I look at alpha equals 0, my objective function is the EY bound. If I look at the stochastic gradient descent, is the one that corresponds to stochastic gradient descent on the EY bound. So basically, the takeaway message is that now we have a new bound, the VR-IWAE bound, which will provide us with theoretical guarantees. Unlike before with the VR bound, where you had a biased stochastic gradient scheme, a biased approximation of your targets, now you bypass those problems and you can provide theoretical guarantees for the whole scheme. This impacts already existing schemes because now you can tell, yeah, okay, what you're doing has like theoretical foundation. And secondly, this VR bound will interpolate between the IWAE bound and the evidence lower bound. So this tells us, okay, playing with alpha is actually doing something that, you know, people were looking at the IWAE bound, they were looking at the evidence lower bound, where we'll have a bridge in between these two variational bounds. Okay. So we found this object, which looks very interesting. Let's study. Let's try to get an understanding of what goes on as I play with this value of alpha. Does it make sense for everybody so far? Yeah. So let's move on to the theoretical study. In order to study theoretically my VR bound, I'm going to look at a quantity which is called the variational gap. Basically, it's my bound minus my targets, the marginal log likelihood, which I've defined here. So this is always non-negative, non-positive, and it's going to be equal to 0 if I've reached my targets. And basically, I can rewrite this under this form, where here I just write under this form because it makes this quantity appears, which I'm going to refer to as the relative weights. So the relative weights, they are my weights from before, the joint divided by my approximation, renormalized, okay? Because now I'm taking the expectation here. So I divide by the expectation. And if you just write down what this means, it just means that I'm looking at my posterior density divided by my approximation. So when those weights are 1, this is 0. So this is what I was telling you makes sense, right? If my posterior density and my variational approximation are equal, then my variational gap is 0. So I'm going to look at this variational gap, and in the rest of the talk, I'm going to be dropping the dependency in X in the weights. This is just for convenience because I don't want to have it everywhere, but you guys deep down will know that it's there. Okay, so we will look at two complementary studies of this variational gap in 2 contexts. The first one will be letting N, because you know my VR it depends on N, on my variational gap depends on N. I'm going to look at what happens when N goes to infinity, and I'm going to keep for now the dimension D of Z fixed. So I want to know, does it play the role to increase N, and is that role impacted by alpha? That's going to be my first question. My second question is going to be, okay, I've kept D fixed. What if I look at N and D as they go to infinity? And I'm going to specify some regime for N and D. They're going to go to infinity, but under some rules. So basically, if you're starting to be a bit tired at this stage, what you need to know is that I'm saying those studies are going to be complementary because the first one will be tailored from low to medium dimensional settings. So it's an analysis for what happens in low to medium dimensions. And the second one will be tailored for high dimensional analysis, okay? So that's why we're saying those studies are complementary. Okay, so let's start with the case where N goes to infinity and D is fixed in a variational gap. So why did we start with this case? Not just because, you know, we're like, oh, we want to keep D fixed to something. It's because in the literature, a special case was had already been studied. So if you're aware maybe of like this paper by Madison et al., NeurIPS 2016, and Dom-Conchedon in NeurIPS 2018, they've been looking at the variational gap for the IWAE bound. Anyone has heard of this paper? No? Okay. So informally, what they prove in this, the second paper is a refinement of the first one. What they prove is that the variational gap, when alpha equals 0, so when looking at the IWAE bounds, can be written as this expression. So basically, it's minus a certain gamma squared, put to divided by 2n plus a term that is negligible in front of 1/n. And gamma 0 squared, I forgot to correct it, is the variance of the relative weights. So it's the variance of the weights I mentioned to you before. Basically, the high-level perspective is that if you increase n in this expression, you will see that n is very beneficial to reduce the variational gap. So it motivates playing with n and try to increase it, okay? And now that we've got this analysis, we were like, okay, can we adapt this framework to our more general bound? Is it making sense to everybody? Yes. Yes. Okay, good. So let's look at what happens for our more general VR-IWAE bound. So I'm going to be in my range from before. So alpha is between 0 and 1. 1 is excluded. I'm going to introduce some quantity here, some quantities here, a gamma alpha squared. You don't need to worry too much about what it is. Then under some condition, I say that my variational gap can be written as follows. So basically, what goes on in this expression is that you've got two main terms, this one and this one. So this one you recognize resembles a lot the one we saw in the result by Donker and Sheldon, right? This one. And it goes to 0 at fast 1 over n rate, and it depends on this quantity here, this gamma alpha squared. And then there is a second term here, which involves the variational bound. This is back to the conversation, minus the log likelihoods. And basically this term is 0 when alpha equals 0, and it will decrease away from 0 as alpha increases. So basically how you interpret this is that as you will increase your alpha, this is going to stray away from 0. 0 is your target, so you get more and more negative. Okay. So what this tells us is that the hyperparameter alpha is going to balance between those two terms. Okay, and so that because alpha will play a role here, and alpha will play a role there. So this means that playing with this alpha might actually impact what goes on in the bound. So it's giving us a few insights about the behavior of the bound as a function of alpha and n when d is fixed. Okay? Yeah? Very silent crowd today. All right. So here I set some conditions, and you might be wondering what those conditions are about. Do they depend on alpha? If so, how? And as it turns out, those conditions, they exactly generalize the one that were in the paper from Donker and Sheldon, and they do not get more restrictive as you increase alpha. So basically, as you move from the case alpha equals 0, which was what they did, if you increase this alpha, those conditions, they do not get worse. So it promotes the use of alpha that is not necessarily 0, basically. Okay. And yeah, and one of those conditions permits to control this term. All right. So I don't know if you're excited about this result, but I am, because it's to the best of our knowledge, this is the first result that tells us how alpha may play a role in methods that involve alpha divergences in variational inference. Up to now, people were working with the VR bound, so they had no understanding yet, no grasp of how alpha might play a role in this bound. So this is super exciting. Let's see an example. So I'm going to assume that my weights, my relative weights, have a very specific form. I'm going to assume that they are log normal of this form. Do you guys know what log normal is? Yes? Yeah, okay. So everybody's saying yes, but basically it's quite straightforward. It's just you assume that the log of your quantity is going to follow a normal distribution. So here you've got SI, oops. Here you've got SI, which are IID random normal IID normal random variables. You multiply them by standard deviation term, and you've got a mean. And this is done in such a way that if you look at the expectation of your weights, it's equal to 1. Okay, so you're going to assume that the weights are of this form, and when you are in this particular case, you can evaluate all the quantities that appear in your in the theorem I was giving you before. Remember, you had the error term and you had the gamma alpha squared. Okay, so if you work under this assumption on the weights, then you can say that the error term is of this form and the gamma alpha squared is of this form. And basically, now I'm going to give you an example within an example where I can write the weights under this form. So if I take the pursued density to be a normal, distribution with mean theta. And if I take the variational approximation to be a normal with mean phi, and if I set my parameters theta and phi to be 0 times the unit vector of dimension d and phi to be the unit vector of dimension d, then I will be under this condition, under this assumption on the relative weights with sigma equals 1. Okay, so I found a toyish example that fits into this framework. And now I want to see whether or not my prediction, the prediction I'm making on the behavior of the variational gap is true. Okay, so to do this, my variational gap, I'll have an approximation of it using Monte Carlo estimation. And my theorem 1, I'm going to express it through function of this form. So basically, this is my prediction, okay? And I've got a term that is negligible in front of 1 over n. So I'm just going to say it's c divided by n, and I'm just going to play with c. Does it make sense? Yeah, makes sense? Okay, so here are the results. So I'm looking at alpha equals 0, 0.2, 0.5. And I'm looking at dimension g equals 10 and g equals 100. So if we look at this plot, in blue, you have the Monte Carlo approximation, you've got this. And in violet, you've got the prediction. Do you think the prediction is a good prediction of the behavior of the variational gap on this one? Does it fit?
As long as n is large.
There? I mean, even for like smaller value of n, no? It's pretty good.
I like that.
Please, you can come here. Not too bad. In this one, not too bad. In this one, then your comment applies, right? It's like, it's not so good unless n is really big. This one as well. And if you increase the dimension, even the case alpha equals 0.5, which was not doing too bad here, becomes not so good. You need n to be really big in order for your approximation, for your prediction to reflect what's going on. Why? Like the question is like, why is this happening? Well, there's something I kept a bit hidden. I keep like hiding things from you guys in this talk. And what I kept hidden is this. Here in the gamma alpha squared, so the term that appears in my 1 divided by 2n quantity depends on d, and it's a bad dependency in d. It's like exponential in d. So this means that my theorem 1 may not capture what happens in high dimensional scenarios. That is to say, we might never use an n that is large enough for this prediction that we made to be accurate. So this is exactly the point that you are making. Oh, I need n to be really big. Here's the reason why. Because I'm exponential in d in the term that appears as a factor. Okay. So this begs the question, okay, can we analyze what's going on in the variational gap as both n and d go to infinity? We need to take into account the fact that there's a dependency in d. And this brings us to introducing here a dependency in d and trying to perform an analysis of the variational gap as both n and d go to infinity. All right, all clear so far? Yes. So there's more theory coming, so you guys need to brace yourself. Okay, so let us have n and d that goes to infinity in the variational gap. The intuition we had in the paper is to say it's actually reasonable to assume that the distribution of the relative weights will have a log normal distribution of the form that we've seen before. So this means it's actually reasonable in practice to have to be in a situation where theorem 1 will not apply. Okay, so we're going to assume that the weights, they are log normal or approximately log normal, and this gives us a theoretical study in 2 steps. First, we look at the log normal case. So we're going to see what happens in the variational gap if we assume that we're exactly log normal and we let n and d go to infinity under some condition on n and d. And secondly, we are going to say, okay, maybe log normal doesn't reflect what happens in reality. We're just going to try to see what happens, what we can say on the variational gap if we're approximate log normal. So approximate log normal is something that we've defined more precisely in the paper that we will see, but basically, let's see if we can say something in that case as well. Okay, so log normal case, here's the result that we have. So assuming that my relative weights are of this form, so this is the one from before, then I can write the following asymptotic regime for my variational gap, okay? So informally, like this is, now we relax a little bit because it's already been like 40 minutes in the talk. Informally, what this result says is that as n and d go to infinity, assuming that log n divided by d go to 0, here's the behavior of my variational gap. So there's a leading term here, which is minus d sigma squared divided by 2. And then you've got terms that go to 0. So basically, this is log n divided by d, and under our assumptions, this goes to 0, and this is like the square of it, and this also goes to 0. So we really are dominated by this term. And if you compare with what we had in Theorem 1, what you observe is that while increasing n will play a role in this bound, in fact, it's going to do so by a factor which is negligible. So what we had before is like, wow, n's going to help us so much in reducing this variational gap is not so true if you work in the conditions of this Theorem 2. And secondly, this term, this is contrary to before, it does not depend on alpha. So this means that the conclusion that we reached could have been like, okay, let's maybe put alpha equals 0 in there. And then we at least, we don't have this, we don't go too far from, 0 as a function of alpha. Well, this term does not we don't even have a dependency in alpha. So this problem that we encounter of going to minus infinity sort of with the dimension is something that applies to the IWAE as well. So if you're from the IWAE community, this sends quite a powerful message. There's a problem even for IWAE. It's not something that you could attribute to methods involving alpha divergences or something. It's like something that is common for all the values of alpha we're considering. So what's going on? What's the matter? What's the problem? Why do we get this kind of behavior? Well, in a high-level perspective, we have a weight collapse. So our variational gap, which we're hoping that would behave better than the evidence lower bound, like with n, it doesn't do so. So the variational gap behaves like the evidence lower bound minus the marginal log likelihood. So the gain you were expecting to have, you don't have it. Like working with the variational gap is the same as working with the evidence lower bound, okay? As long as you are under these conditions. So what is this condition saying? This condition is saying that if you hope to not have this weight collapse phenomenon, you need to at least have n, which grows exponentially with d. So this is not very good news because you need an incredible budget to be able to not be in those conditions. All right. So that's for the theoretical study. And if we now go back to our Gaussian examples, and if we try to compare the two approaches that we've seen, so the first one, which was Theorem 1, and the second theorem, which is this one under this assumption, then here are the curves that we get. Those one we've already seen, and here are the ones for Theorem 2. So I still have alpha equals 0, alpha equals 0.2, and alpha equals 0.5, and I'm going to look at dimension 10, 100, and 1000. So what do you think this time?
It's pretty good.
With your good glasses, do you think Theorem 2 is a good approximation in high dimensions? Yeah, okay. So this means that what we've predicted, in fact, reflect the reality in high dimensions. Okay. So like I was saying before, looking at just the log normal case might be a bit of a limitation because in practice, you can't really expect things to be log normal. So we looked at an approximate log normal case. And by approximate, basically all you need to know is that instead of having SI that are normally distributed like before, I'm going to write them under this form. And I'm going to make assumptions so that as d goes to infinity, this is going to look like a normal distribution with mean 0 and 1. So this will change slightly the expression of my weights. And I'm going to say that approximate log normal weights are weights of this form. So you don't need to look too much into them, but basically, whoops, I will still have like here standard deviation term, and here I will have a mean term, which is a bit different from before. And if I now look at the theorem, the theoretical result that we get in the approximate log normal case, well, basically what you need to take away is that we get the same sort of behavior. So there is a weight collapse phenomenon telling me that the variational gap, when I work with approximate log normal weight, is going to behave like the evidence lower bound minus the marginal log likelihood. What's the difference? The difference in this is in this term here. So previously I was telling you, if we're hoping to get out of this weight collapse, we need to be to have n, which is at least exponential in d. In the approximate log normal case, we need n to be exponential in d one-third. So the condition is less bad as it used to be, but it's still a bit stringent. But it tells you that okay, maybe log normal is like really bad, but approximate log normal or some other cases that we might be able to study might not have such bad conditions in practice. And yeah, this is like, so this is the term that we have, and basically there's no dependency in alpha left in this term due to our conditions. This is just so that when you see the curves, you know, you had a bit of orange. Now I'm going to put all the alphas together, basically. Okay, so can we find an example that was used in the literature that fits in our setting? So Joe is the one who kind of found out that we could fit this example, and we're super happy because we have an example in which all our conditions are satisfied. And basically, what you just need to know is that so you have a specific pursuit density and you know a specific approximation. And if you work with these assumptions, you can have that your relative weights is satisfied the form I gave you just before. And here, all the parameters, they have a specific expression, which is written here, and they depend on a parameter lambda. Basically, the thing that you need to know is that if you consider your optimal parameters, okay, so you've got theta and phi. If you take theta star and phi star, you're still going to be in the conditions of our theorem. So this sends kind of some sort of important message. Tells you that in this particular problem, even though you are at optimality, you are in the conditions of application of this approximate log normal assumption. Okay, so this means that you have two competing approaches. One approach, which is theorem 1. Okay, in that case, you can compute things in a tractable manner and observe that you have an exponential in D sort of behavior. And you've got theorem 3, which is the approximation that we were saying is for high dimensional settings. Okay, so yeah, here are the plots. So dimension 20, 100, 1000, alpha equals 0, 0.2, and 0.5. Our experts, what do you think? Dimension 20, is that a good approximation?
Yeah, very good.
Okay, very good. Dimension 100.
Pretty good.
Pretty good. 1000.
I would say good.
Good. Not very good. No, what do you think? Like when n is between 0 and 100, not so good. Look at this. I don't know if you can see. This is 1 exponential 30. So it's pretty big. So it's not like, oh, it's gently going there. It's not gently going there. So basically, this tells you that in high dimensions, things are starting to go wrong. What you were saying, oh, not too bad. So this not too bad is actually what theorem 3 was about. It's like now log n divided by d 1/3. It's not log n divided by d, but there's still something at play here, and you need to have a big N in order to mitigate this effect. On the other hand, so here are the plots. Yes, we also looked at like a perturbation of the optimal parameters. Let's look at this one where we perturb like our ideal parameters to see like what's going on. What do you think? This one in dimension 20. In green is the prediction by theorem 3.
Good.
Good. Did you think this is good? The end part?
No, I just don't understand why is it like it seems better for high dimension and lower dimension.
Why this is better? Like the approximation here?
Yeah.
This is the prediction we're making for high dimensional settings. This is the prediction by Theorem 3.
Oh, right. Okay.
So this is
Great,
this one. This is this one.
Okay.
And this one was like the Theorem one, which is low to medium dimension. So hopefully, if you just look at this once, you see that as you increase the dimension, the range of the n, you know, like that you need, like that you're using, is getting bigger and bigger. So this tells you that you have this like log n divided by d1, the thinking that needs that. Unless this does not go to 0, you will fall in what happens in Theorem 3. Okay? Yeah, good. The rest of us, of you guys are okay with it because I'm just grilling him over here. But okay. So those experiments so far, we knew the posterior density and we could evaluate most of the things. We have another example where we looked at where we don't have the posterior density. It's only known up to a constant. So we looked at variational autoencoders on MNIST datasets. And the first thing we looked into is that, okay, are the relative weights looking like they're becoming log normal? So this is an example. This is just for one data, but we saw it across several data points. So if you look at the QQ plot, so you're trying to guess whether or not the distribution of the relative weights is starting to look log normal. So this is dimension 5, 10, 50, 100, 1000, 5000. So I'm going to pick someone else now. Chris, do you think the distribution of the relative weights is starting to look like normal as we increase the dimension?
Yeah.
Yeah. Good, right? We're doing our job pretty well. Okay, so this means that it might actually be reasonable to make the assumptions that we make, and now we want to check, whether our prediction in Theorem 1 and Theorem 3 they apply in the context where not everything is can be computed, right? There's normalizing constant that we don't know. So here is like for Theorem 1. So okay, I've asked you too many times, so now I'm gonna ask someone else. Eugenio, what do you think? In dimension 50, is Theorem 1 a good approximation of?
I would say yes.
You would say yes. Okay. Dimension 100.
Yeah.
Still pretty good. Do you see a difference between those two still? Yeah. So this is just to tell you that in Theorem 1, there's the dependency in alpha, right, that you need to factor in. So in fact, you see that, you know, as you play with the rule of alpha, you might have some differences between alpha equals 0 and alpha equals 0.5. So it's just like a side remark. And okay, dimension 1000.
It's getting worse.
It's getting worse. Everything's getting worse. Indeed, good comment, Eugenio. Okay, now let's look at Theorem 3. What do you think as the dimension increases?
It's better.
Yeah, I tried to push you guys so that, you know, you've got the right answer. So indeed, you see that Theorem 3 looks like it applies as you increase the dimension. One comment on this, look that here we had to still go pretty high dimension for this to happen. Okay, so this is dimension 5000. And what we see is that what looks like it changes that it applies, but for certain range of values of n, and these values of n, they become like bigger as you increase the dimension, which is really this idea that you've got a link between n and d for this kind of weight collapse phenomenon to happen. Okay, I've got like 5 minutes left. So we've spoken a lot about the VR-IWAE bound and its studies. And you could be like, okay, this is one part of the problem. The other part of the problem, which I am more interested in, is the training. What happens during the training? So we've got a few insights about this. And the first insight that we have, so again, this is if you're a bit familiar with the literature, is that if you play with alpha, you will in fact be able to improve on the signal to noise ratio of your parametrized estimated gradient. So I don't know if anyone's familiar with this. No? So basically, signal-to-noise ratio is a way to measure the quality, sort of your reparametrized gradient estimators. And previous results show that if you look at the training of the parameter phi, when you use the IWAE, you've got a bit of a problem, because as you increase n, the signal-to-noise ratio is going to go to 0. Okay, so this is kind of bad news. We're trying to learn phi, but if you work with the IWAE bounds, you're not learning phi very well as you increase n. So it's a bit counterintuitive as to what you would want in practice. As it turns out, if you play with this alpha, you can sort of remedy this thing. So this is what is written here. And it tells you that trying to learn with alpha might actually have good impacts in practice. The second thing, again, is if you're a bit familiar with the literature, the doubly reparametrized gradient estimator that was developed for the IWAE can be extended to the VR-IWAE bound. This estimator was used to remedy those signal-to-noise ratio problems. Basically, what I want to say here is that training with the VR-IWAE bound might be a good idea, because the signal-to-noise ratio problems that was observed in this paper seems to be alleviated, and the doubly reparametrized approach, which was developed by Tucker et al. In ICLF, generalizes. So the VR-IWAE bound is literally the good extension, and if you try something for the IWAE, you should try to see whether or not it works for the VR-IWAE bound. This is the final plot, just to shed a bit of hope. So this is still the MNIST, and we looked at the approaches like the reparametrized and doubly reparametrized approach for various values of alpha. We kept it low dimension, and basically we observed that it does play a role. So everything that we've seen so far kind of makes sense in low dimension, and in particular, in this one, we see that the optimal value, this is negative log likelihood after training, is definitely not 0. So it's important to have this flexibility when you're trying to learn. Okay, conclusion, everybody is letting out a sigh of relief. What have we seen so far? So we formalized and motivated the VR-IWAE bound. We've seen that it's the theoretically sound extension of the IWAE bound, which corresponds to the case alpha equals 0. It provides theoretical guarantees behind existing schemes. Okay, so people can do a VR bound schemes without worrying too much now that there's a VR-IWAE bound, and it enjoys other additional desirable properties in terms of training, so signal-to-noise ratio, and you have also doubly reparametrized estimators. We've given 2 complementary analyses that shed light on the conditions between the success or potential failure of the VR-IWAE bound methodologies. And we've seen that those conclusions, they apply to the IWAE bound. So our work is in fact very tied to what happens with the IWAE bound. We've looked at several examples. You guys have discussed and commented on those examples. And just want to finish with some open questions. First question is like, okay, this weight collapse behavior, does it happen beyond the cases that we've seen here, beyond the log normal and approximate log normal cases for the distribution of the relative weights? How does it affect the gradient descent procedures? And are we able to use the fact that the IWAE bound is the correct extension of the IWAE bound in more ways than we did in that paper? Because what this tells us is that, okay, maybe we should try all the methods that have been used to improve on the IWAE bound, but maybe we should try them on the VR-IWAE bound. This could be to build better gradient estimators, or just to play with this Q-phi, which I didn't give you too much detail about. Like we didn't delve into how general this Q-phi could be. Okay, so that's it for me, and thanks a lot for your attention. If you have any question, feel free.
Like kind of correct me if I'm wrong, but I guess trying to like get intuition from the work. So normally if you have like elbow, you do like the same one, so you log in and then log weights and then like must be behaved. And then if you want to go like I-way,
Yeah.
you take the log out and you have some like inner kind of expectation indirectly in weight space.
Yeah.
For like alpha equals 0.
Mm.
And then when you're doing your theorems, you're saying like if you don't make n grow large enough with dimension,
yeah,
there's no point in doing that because you're basically just doing alpha anyway, because like I guess it becomes degenerate directly in weight space.
So that's what it's saying under some conditions, right? So if your weights are log normal or approximate log normal, this might happen if you're, for example, very far, like your approximation is not so good. So if your weights have a lot of variability. Yes, yes. So if this is not good, then the sigma, you know, which appears, which measures kind of how much they differ, this is going to be big. Then you end up log normal, and what you're doing is basically doing an elbow. If you manage to put yourself in a situation where the sigma becomes small, so through group training of the evidence lower bound, for example, or something, then you might have hope to, you know, fall back in the realm of what goes on in Theorem 1, which we said, okay, it's low to medium dimension because this sigma, you know, as you increase the dimension, very, very likely that this is gonna grow big. Yeah. So this means either you need to play with the variational approximation. Playing with the variational approximation can help you actually reduce the sigma. You know, your approximation, your Q phi becomes closer to your pursued density. So you basically, more works need to be done. I didn't get too much into the detail here, but like in this example, because there's a mismatch, no matter what you do, even though you are at optimality, there's a mismatch between your pursued density and your variational approximation. That's why you end up being approximate log normal. So the way to get out of this is to really work, in my opinion, on the variational approximation. Other questions maybe? Or maybe from the chat, I don't know. Amitis is in charge.
People just thanked you for the talk.
Was everything clear, or yeah? Joe's like super clear, good work. Okay, well, if you guys have no more questions, I suggest we close the session and we go have lunch together. How does that sound? Yeah. All right, let's do that then.
I stopped the recording then. Thank you.
Thank you, Amitis. Thank you so much.